Okay, I might do a quick introduction then. For those of you who don't know Suj, I think he's been at a lot of sim cafes lately anyway. Sujeewa Palagama works at the University of Griffith, or Griffith University, isn't it, up on the Sunshine Coast, and is a medical educator. And he's been to a couple of the SimOst simulation congresses, which is where I met him, and has a strong interest in how artificial intelligence can be used in medicine in both good and bad ways. So I'm really looking forward to this talk, and thanks for giving up your time, Suj.
So good. Very happy to share. Just disclaimer, I'm going through the last couple of sim cafes. I'm not an expert, just as a disclaimer there. Just a mere PhD candidate, that's all. Hence why I just mentioned India is our PhD candidate rather than me trying to be an expert on the field. However, it's pretty interesting and it's inspiring for anybody who hasn't really started a PhD. But it's amazingly interesting. I'll try to stimulate your interest as possible. So shall we go ahead? Sorry, I just used my earlier PowerPoint presentation at Griffith University so that you will see Griffith University logo at the same time. All right, so I'll try to cover what is artificial intelligence, and we'll try to cover the applications of artificial intelligence in medicine and some limitations. That are so many. We can just talk days and days about applications and limitations, and just a segue to following discussion how we can go forward. All right, so to talk about what is exactly artificial intelligence is that I think it's best to understand what is intelligence first and how does brain work, just because we have a variety of people from different areas. And correct me if I'm wrong, Joan, anytime, you are welcome. So we call intelligence, trying to be a little bit philosophical / scientific, is that if we have the ability to acquire knowledge through different sensory organs, for example, the way the brain works is that we get sensory stimuli from eyes and nose and taste and hearing, and through our touch sensory organs. So our brain is exposed to a variety of stimuli at a given point of time, and the brain processes all of that information, and on top of that it uses the memories that we have had in the past, and depending on the circumstances we are in, or the location, or the situation, it applies the knowledge it gained through the stimuli, through eyes and ears, and touch, and then it try to um, solve a variety of problems, or try to change our behavior, or make us do certain things which are expected to be the best outcome for that particular situation. So it's basically driven by a positive and negative feedback. So when a child is being brought up, every parent would know. So there are certain things, these are good things, there are certain things which are naughty things or bad things. And then there's a process of learning over many years. And then that results in a certain way of expected behavior, basically driven by the brain. And the way that we do it is through positive and negative feedback mechanisms. And usually they are mostly survival instincts that we have adapted to a human society. And what basically artificial intelligence is almost the same. It's a non-human system to begin with, but it can acquire knowledge through multiple digital inputs. Those digital inputs could be images, or it could be texts, or sometimes sound or speeches, or certain movements even can be categorized as multiple inputs. And then this system can process the information, and it does what is called as learning / machine learning, and it saves all of that in the memory for future use, and applies the same thing to solve a different problem. Usually it's driven by two mechanisms. One is called supervised uh, learning process. The otherwise is called is non-supervised learning process, which will be touching soon. So usually this is a really nice diagram. Karen Howe, she's a um, journalist slash a researcher who usually writes blogs and MIT driven articles, and she has really nicely uh, conceptualized what is AI. So can it see, can it hear, can it read, can it move, or can it reason? So when you go through this flow chart, you can see whether it's using AI or not. So that's for future reference for you, just in case if somebody wants to. And let's talk a little bit about underlying principles of the artificial intelligence. Mainly, the notion of artificial intelligence is attributed to a system where a machine is learning by itself. The underlying principle that is currently used or largely used are called deep learning networks, DNN, or there are different types of deep learning networks. There are convolutional deep learning and then retrospective. There are so many types of learning neural networks. And the reason why they're called neural networks is because they work in a way that the neurons in your brain would work. So most of the neurons in your brain, they are attached to different other neurons. So when one neuron is stimulated, it also stimulates certain other set of neurons, and those neurons stimulate certain other sets of neurons. Sometimes those neurons come back to the first neuron which started that as a positive or a negative feedback. So similarly, in the brain, it's almost the same. And in artificial intelligence based non-human platforms is basically the same. So we have one layer, it's almost like a club sandwich on its side, to quote an article at which was published in Nature. So we have one input layer, and there are a number of hidden layers, which is called, some people like to call it as a black box model of AI. And there's an output layer. So those layers are called neurons, and every layer has connections with the other layer. And the way that it's designed is that humans can decide the number of layers you have, and um, it the machine itself decides how many connections it should make between the different layers. I'll try to make an example by taking just one example from dermatology. So imagine when we are diagnosing a melanoma, for example, if a doctor sees a certain patch on the skin, whenever a patient comes to a doctor, first of all, we are trained as medical students, like, okay, look at the lesion and see whether it comes in the category of a normal benign nevus, or can it be a malignant nevus. There are certain features that we are trained to see. One, it's called ABCD mechanism. So A is the asymmetry. If a certain skin patch is asymmetrical, B is the border. If the border is in a certain characteristic pattern, it might be suggestive of cancer. C is the color. Certain lesions with dark colors are said to be more cancerous than light color ones. And D is the diameter, how it changes. So likewise, there are different characteristics that the doctors would use. At the end of the day, all what you use is a certain set of specifications. And if the specifications come into a picture where it's suggestive of a cancer, a doctor will diagnose it to be a cancer. So basically the same thing can be done by a computer. So a computer can decide, okay, if it's symmetrical or not. It's very easy to see by a computer, and then it can determine what's the border like, because the number of pixels which are colored dark versus number of pixels which are colored light, obviously with that border the computer can decide that, similar to certain technologies that are used in Adobe Photoshop almost. So different character and the diameter and everything can be basically determined by the computer itself. So what it does later is that it when can when you can feed the computer or this AI system a different number of lesions and you label them. So if there is one lesion and if it's known cancer, then we just feed it to the computer, and then it analyzes the characteristics depending on the ground rules that we have put in. And then we feed in another image, and then it is labeled as non-cancerous. So likewise, we can feed in about tens and hundreds of thousands of images to the computer, and then it itself learns from its experience, uh, underlying the ground truths, which is cancerous, which is non-cancerous. And then ultimately, when you feed a new set of data, then it gets to diagnose whether it's cancerous or non-cancerous. And you can check with the ground truth. And then if the computer decides, okay, if it's cancerous, then it takes it as another learning experience. Likewise, after many thousands and millions of iterations, it learns by itself. That is called artificial intelligence. And that is used in deep learning networks. All right, so as I said, we have supervised methods and unsupervised methods. Supervised method is what I mentioned earlier, where the images are labeled, which is cancerous, which is non-cancerous, and then ultimately the computer learns what is a cancer, what is not a cancer, and then assumably it acquires the capacity to diagnose whether it's a cancer or not. That is one way of doing things. The other way of doing things is we just feed the computer with millions and billions of images, and it determines a pattern by itself. So the way that they do it in 2012, Google AI thought that we need to test if a computer is able to identify a cat. So it fed millions and millions and millions of images to the computer system, and then ultimately it um, understood what a cat means. But as we know, a child or a human would understand a cat with a circle and a couple of triangles on top of it, and then it just have a certain pattern, two eyes and a mouth. Even a child would understand it's a cat. But however, a computer might not be able to do that if it hasn't been fed uh, an image that looks like a cat. In other words, sometimes computer might be able to understand the human image. However, it might not be able to understand a human image that is drawn by Picasso, probably. So yeah, it's kind of interesting how the computer sees things, if it's unsupervised. But if it's supervised, you can control the way it sees things, or decides things, whether it's type A or whether it's type B. All right, so that's the underlying principle. And just to uh, talk a little bit about AI, there are so many variety of uses of AI in medicine. So just to categorize them on a bird's eye perspective, there are certain, like if you think about a progress of a patient, imagine if you are a patient, if you have a problem, then you would go to a GP. And then the GP would diagnose if you have a condition, or to see whether you are healthy. And then if the GP is not sure about it, then you'll go for a consultant diagnosis, for example, if it's a melanoma. And then once the diagnosis is made, then the management is planned, whether to excise a lesion or just to watch and wait, and then or to whether give treatments. So in that process, you have different steps where a patient is taken through to a GP, and GP would decide whether is he or she going to treat it, or then there's another decision point where he or she needs a second or a third opinion, and then after that the patient is managed. And in hospital setup, what happens is when a patient goes to a hospital, the patients are categorized depending on the severity of the conditions. Like, let's for example, if the patient says it's a chest pain, it's suggestive of a myocardial infarction or a heart attack, the patient is expedited and then taken in as soon as possible. And if it was just like a leg pain, which is non-significant, which doesn't have a clinical significance, then they are put down in their category. So it's called category 2, category 3. Depending on the category, the wait time changes. And at the same time, a similar pattern of wait time applies when you are seen by consultants as well. So there are, depending on your circumstances, you just have to have a certain wait time. Sometimes you are seen within 1 week, sometimes it'll be about 3 months. So what UK NHS system has done is that they have trained AI system to triage patients. This whole process is called triaging. So they have produced some evidence to say that AI is capable of triaging patients. In other words, determining which patients need early care, which patients can wait a little bit longer. So that's triaging. And in terms of diagnosis, I'll touch on diagnosis much in breadth and depth in later slides. And assisting medical treatments, then again, about determining management, determining ICU management, and then which patient needs early care when you're managing patients in the ICU had been again helped by the artificial intelligence. And in patient surveillance, when you send the patient out home from a hospital, certain patients have to travel far and distance from a main care offering institution. Depending on their circumstances, AI have been demonstrated to have some positive impact on patient surveillance system, and again for prediction of survival as well. So in a way, if you about prediction of survival particularly, if you have a AI system that suggests, okay, this patient has a higher prediction of survival versus another patient who have like 10% chance of survival, then it's very reasonable, or it can be argued as it's reasonable to attend to the person who has a higher uh, survival prediction than the 10%. But then there are certain ethical issues why if you can't attend to that 10%, then there are certain ethical issues as well. So just trying to let you know that there are positives as well as negatives in that as well. Right. So in terms of diagnosis, that's the key area in medicine that the AI had some great achievements, and there are the areas that the AI had been effective is exponentially increasing over the past couple of years, especially. Although there had been researchers for about a couple of decades, it's the past, like since 2013, 14, 15, and 16. Afterwards, it's like almost exponentially, almost like an avalanche of research articles are being published. So just to take a couple of examples, pneumonia. So again, chest x-ray, when you're looking at a chest x-ray, there are certain patterns that the doctors would look for in order to make a diagnosis, whether it's pneumonia, whether it's a collapsed lung collapse, whether one part of the lung is collapsed in, or whether there is presence of cancer or not. So there are certain patterns that the doctors see. Again, it's just basically image processing, and those are the three main areas that the AI had proved to be very effective. So AUC means area under the curve. So basically, when you're diagnosing a condition, we refer to it as a diagnostic accuracy. So if the diagnostic accuracy is nearing 1, well, if it's 1, it's a perfect diagnosis or perfect diagnostic accuracy. And if it's nearing 1, that means the diagnostic accuracy is better. So for example, if I just take a crude example, which might not be the best example, but diagnosing of melanoma, if a GP can diagnose it in the accuracy of 0.5, and if a consultant would be able to diagnose it, let's say 0.8, so that means the diagnostic accuracy of the consultant is more than the GP. Where AI would come in is that if the AI can have a diagnostic accuracy of 0.7, that means it's much better than a GP, but not so much better than a consultant. But if the diagnostic accuracy of AI system is more than the consultant, that means it's far better than any human can ever do it. So those are the examples where AI applications have been able to outperform radiologists and dermatologists and sometimes even ED physicians that the research are proving too. So, for example, AI applications have been proven to be effective in identifying liver metastasis in CTs, and brain scans for hemorrhages or acute or chronic, and cancer detections in mammograms, and in dermatology and ophthalmology. Basically, the list is never ending. It goes on and on and on. So what it has proven is the fact that computers are exceedingly performing better, and then their capacity has been improving, especially during the last couple of years, uh, in a way that it can even outperform a human when it comes to image processing. These are just some examples for medical diagnosis. And not just the diagnosis, as I said earlier, we can uh, demonstrate that the AI is capable of better managing patients in terms of triaging, and then sometimes better um, managing patients in terms of ICU care, and better managing patients in terms of surveillance. So likewise, there are different areas that the AI has been exceedingly outperforming human capacities. So it's nice to talk a little bit about advantages, what the advantages it brings. So mostly, as I said in my example, in between GP and consultant, sometimes if a patient is in a rural setting and a GP is not sure if a lesion, whether it's a cancer or not, they can probably get some help from AI-based technology. And another example is if they need a second opinion, or if in certain areas in Australia, sometimes a specialist would come in once a week. So until you get a specialist on site on the next week, then you just have to understand, you need to make a decision whether are you going to keep the patient until next week, or are you going to make the patient go to a main center within the state. So those are the decisions that the GPs have to make, and a platform like an AI would help their management of the patient. And in the same time, increased efficiency is another advantage AIs can bring. Again, time to train the thousands and the thousands, and sometimes even millions and billions of images that it can process within a small fraction of time is again a massive efficient factor for AI. And again, time to deploy. If you have one AI-based system that is exceedingly outperforming in one geographical location, it's very easy to copy and paste the whole system on another place. Basically, that means you can improve the efficiency in that way, because training a consultant or a specialist, not easy job. It takes almost like about 6-7 years to have that capacity in terms of diagnosing accuracy and then management to become a consultant. But if you can help that, and if you can cut that time to a certain fraction by using an AI based application, that'll be better. And the capacity to analyze large number in a relative small amount of periods. For example, if you have, there is a certain limit that the humans can work. If you have like 8-hour shift, there is a certain number of x-rays can a radiologist look at. And then there is a certain um, financial burden to the system if you are hiring more and more radiologists. But if you have just one system where it can churn out so many images, that's again financially beneficial for the system. Hence why it might be cost effective as well. And another option would be a streamlining of healthcare, triaging, prediction, and survival analysis. So whilst the advantages are seemingly great, there are certain disadvantages as well. The, there are many. I just selected a couple of here. Yeah, one example is this. So as I said in my previous example, when Google tried to make a computer understand what does a cat look like, whilst it was happening like that, they used to identify humans and animals as well. So unfortunately, in a certain circumstances, a computer learned to identify um, African Americans as gorillas. So that had been totally unexpected, and that was the reason why they shut it down, that whole project. That is one example of what happens when the computer is allowed to learn without being supervised. And there's another thing is, when you're making those labels, there is always a certain bias that are incurred in making those applications, and there is certain bias that there is inherited due to statistical models that they use anyway. So there are various kinds of bias that are incorporated in AI-based system anyway. So that is one limitation. The other limitation is, most of the data that they use or that they feed into the AI learning pathways are the data that they already have. For example, um, if an AI system is developed to identify a melanoma in America, and then if it happens to be mostly Hispanics in origin, then computer becomes really capable of identifying a melanoma, which is a dark colored lesion, on a Caucasian person. However, if you try to use the same system to diagnose a melanoma on an African American or an Aboriginal person in Australia, it might not have the same capacity. So again, generalizability is a problem there. Unless if you have a perfect data set that the computer can learn from, and in that case, then extrapolation or application would be again a feasible thing. And there is one side of application and limitation. And on the other side, whilst the avalanche of researchers that churning out so many research articles saying that the computers are great in diagnosing and diagnosing and diagnosing, there's a notion of overdiagnosis as well. Overdiagnosis is defined as diagnosing something that wouldn't really harm the patient. So basically, you are trying to label a person with a certain condition, otherwise that wouldn't harm. Best example is prostate cancer. So it's a cancer. I'm not generalizing. I'm talking about the 100%, but majority of prostate cancer is a cancer that you can die with rather than die from. So what I mean is, patients can live with prostate cancer but wouldn't even know whether they have it in the first place. And most of the cadaveric studies have proved that a significant proportion of population of men did have prostate cancer at the time of their death, although only a smaller fraction of them were actually diagnosed to have prostate cancer. So that's called a diagnosis that you can live with um, rather than die from. So the problem is, if you diagnose a person to have a prostate cancer, a condition that you can have a seemingly normal life, then with that diagnosis, there are so many things that happens afterwards about the psychological well-being, about the mental and social well-being, and about the treatments that otherwise would have never happened if not to have diagnosed that disease. And over treatment, there are so many things, and the burden to the society and the expenditure, there are so many things that comes with the notion of overdiagnosis. Therefore, when everyone is so, to use the layman's term, gung-ho about diagnosing certain things, there is always a certain burden, a certain fraction that we actually do overdiagnosis is one problem as well. And then the other thing is, although AI is capable of diagnosing something using just an image, when a doctor diagnoses something, that usually factors in a lot of other things. For example, doctor would never diagnose by just merely looking at one image. They would think about the history. They would take into consideration of their family history, if there is genetic predisposition, if there had been any past medical histories or surgical histories, and they factor in all that information into make one correct diagnosis rather than just looking at one image. Therefore, mostly, if you take the whole clinical pictures, doctors tend to be more accurate than relying on just one image, which can lead into diagnostic errors. So again, diagnostic error is one problem. And then the problem is, if let's say if there's a diagnostic error, and then who is responsible for that? So is it the company who made the AI application, or the developer, or is it the company who gave the data to be trained, to train the AI application, or is it the hospital that utilizes this AI platform, or is it the doctor who used this AI platform to make that diagnosis, or is it just the data which are wrong? So basically, we don't know whom to blame to, because, and the other thing is, AI is not an entity that you can um, have a legal case against. Therefore, there are legal challenges. And then the other problem is privacy of data and ownership of data. Usually under Australian legislation, the ownership of data is with your institution. For example, if I get a chest x-ray in a hospital, the owner of that chest x-ray is the hospital, it's not me. Therefore, how many institutions can sell those data or use those data, misusing, and then privacy? There are so many other aspects that had never had any implications before, but with the help of AI, now it's all exposed these days. So there's many limitations and many areas that needs further scrutinization, and policies should be made on. So it's quite interesting, the great advantages of AI, as well as the limitations and the issues and ethical issues of AI as well. So the way forward is, what we can say is that AI is here to stay, and it's a growing phenomenon, and it's the human nature. That's how the society evolves. So once upon a time, we were, like so many thousands of years, we were just hunter gatherers. Now we are sometimes, asking a car to come to ourselves, to us. Like, for example, if you just use the Tesla, you can just ask it to come from the garage. So that's the way the society goes. So there's always a certain development. At the same time, those developments would have positive attributes as well as certain limitations as well. So we need to understand what are the limitations, and how can those advantages be harnessed to bring in a better outcome for people as well as the society, keeping in mind their limitations. So that's my take-home message, and I'm very happy to have a discussion about it.
Okay. All right, I'll turn my video back on as well. Thanks for that, Suj. Does anybody have any questions or comments? Or is everybody going to be shy and make me talk again?
Yeah, no, I'll get in there. Right? Excellent presentations, by the way. Thanks for this. Brilliant stuff. It really is very, very apt and appropriate, and the timing is spot on, right? This is an area that is going to be of significant focus and needs to be of significant focus. Some questions I had first, and then some observations. Are you aware right now of how AI in the healthcare medical field for diagnosis is approved for use in any way? Is there anything that's done at the moment that says right now we can use this for diagnosis, or really is it fairly subjective still?
For the time being, okay, in terms of evidence, UK NHS system has used Babylon, which is a triaging AI-driven system to triage their patients. So that's one example. but mostly most of the evidence that I had in my presentation were basically research. So about the FDA, to talk about US system, because most of them are coming from Stanford.
Yep.
To get FDA approval, you need to have so many iterations, and then you need to study the implications of a lot of other things. So basically mostly on research level. However, there are certain health systems that currently are thinking, including Australia. We here are thinking about using at least AI-based systems and to deliver some research outcome so that we can demonstrate whether it's capable or not. So to tell you directly, in Australia, we don't have any AI-driven system so far, but there are so many AI-based researches that are going on in terms of healthcare. And there are so many proposals going on as well at the same time for the delivery of healthcare. But in other areas, for example, food technology and fruits, and identify which are ripe and which are not ripe, it's already being used in Australia to a large extent.
Yeah. It seems like just from what you were saying and thinking out loud, there's almost multiple dimensions, but three dimensions stood out in terms of the correctness or validity of AI or scales of it. One was the suitability of the algorithm, depending on what you're doing. If you're just categorizing things, it might have a linear type algorithm. If you get more sophisticated, there might be different. So must be, but I haven't seen anywhere that says, if you're doing this, here's the type of algorithm that you need to use that's been recognized as the standard for a particular application, right?
There's not.
No, eh? So
No.
the suitability of the algorithm and the type of algorithm. The second is the sophistication of the algorithm, right? To what granularity, what resolution does it go in order to do the diagnosis? And the point you made about a child can tell a picture of a cat and recognize it, whereas we have more trouble in AI. It's sort of highlighting the fact that the perception element, which is a function of the sophistication and the type of algorithm, is fundamental, right, to getting it right. And we still are in the gray area in that part of it. So that's the second thing. So the type of algorithm, the second, the sophistication of the algorithm, but then underlying all of that, the point you made about the access to data, right? So if you have all the data, then you can apply those and you get a good outcome. But you need the three legs of the stool, right? You can't just have any one or two. The quality really comes when you bring those three things together, and the challenges associated with that. And the interesting thing is that this challenge in AI is not just in healthcare. This is across the board, right? You think of autonomous vehicles, you think, anywhere you apply AI, it's the same foundational principles. And the challenge is finding the mix. And I really think that this is going to change, as you pointed out, our policies, our governance frameworks, our legislative frameworks, because it's so critical that you can make a life and death decision based on this stuff. We have to have those things in place. And I think, and again, coming back, CMOS, the CISA, Systems Engineering Society, the things that we should be focusing on in this area is helping support those aspects. How do we put in place the right framework so that we do have these things happening in the right place? And I think the challenge there is going to be that it's not just about technical correctness or algorithms being right, but it's about the ethical aspects, environmental aspects, social aspects, cultural aspects. It goes across the board. And it will force a change. I think, and I want to get your thoughts on this in terms of, and I think I said this before once, our legislative frameworks, from a punitive after the fact approach to a proactive, preemptive governance framework that brings in specialists that understand the concept, don't necessarily understand the technology, but approve the use of the technology because the concept is what's important over here. So just some thinking out loud thoughts there, right? So back to you and Dale,
I couldn't really agree more. Like basically, everything what you said is true. To make it more, make the matters worse. Nobody really knows how can a deep neural network come up to a diagnosis. Like that's the problem. That's why they call it a black box. If it's a normal statistical model that any doctors would use, you would know, let's say, for example, I'll take one example, say a certain test that they do, an eye test probably, right? When a doctor uses that test, most of the time, when a doctor uses that eye test, they know the probability of that particular test being right. So that's how usual statistics works, and they know the accuracy of that, and they know what probability doesn't really work. So it's a good way, so that the doctor knows, okay, most likely this is the case, and then there is a 0.2% chance it might be wrong as well. It's there for anything as well. That's because mostly it's linear algebra and it's statistical principles. But the problem with AI is that you can't really have a statistical thing because we can't really explain how the computer came up to that diagnosis, because nobody really understands the whole picture of algorithms. That is one side. And the other side, as you said, is application and the social aspect and the legislative aspect and then the policies. And then you need specialists to look at those aspects. So I couldn't agree more.
So in the main, it will probably, not probably, I think it will need to stay as a complementary concept, with the human there really being at the end of the day the decision maker, right? And I think that's fundamental until we get it right. The positive of it is that it actually provides a level of objectivity where human subjectivity might come into play. So for example, if the specialist is having a bad day, right, and is stressed out, having an AI to complement that and actually come up with an initial or a diagnosis that is perhaps might not agree with their initial diagnosis will probably get them to think and say, hang on, maybe I didn't do the right thing over here. So it's a safety factor as well in that regard.
As a tool to be used rather than the sole way of managing a patient.
Good.
Yeah, I've been doing research in this area as well, because that's what my master's is about, the use of AI in education. So I found your talk really interesting because you're looking at it from more of a biological point of view, and the way you described AI is completely different to the way I would describe it, as more of an information system sort of point of view. But yeah, I find, and I think it kind of relates to the talk last week about standards as well. Like my big issue with, and it's not even AI, but it's algorithmic decision making in general, is that we're building these machines which judge everybody the same way, which JB, you just said it's fair. But there's a bit of research around that suggests that people actually like that there's different forms of decision making around. And I know, in Melbourne, in Vic Roads, if you want to pass your roadworthy, you take it up to Sunbury Vic Roads because they don't have a pit. And they've got lots of women who don't know much about old cars. And you're more likely to get a roadworthy there. Whereas if you just have a machine that's doing everything and judging everybody the same all the time, it's really, in a sense it's more fair, but in a sense it's more unfair because you're always going to get the same decision and there's no sort of appeal to humanity that's possible. So
yeah, I was going to say not everybody's the same anyway. So judging everybody the same way isn't always the right way to do it. I guess that's part of the issue as we've talked about earlier.
Exactly right. And human nature, it boils down to human nature, isn't it? But because sometimes we need highly accurate systems, but at the same time, we don't really need highly accurate systems.
Yeah, and then if it is going to be one system, like the biggest thing I worry about is then does it become that the perception of the majority becomes the truth for that system in a sense? And, as we know, it's definitely not, because look at the leaders we end up with.
I think the risk is complacently setting in, and you don't want that, right? You really want to have the human at the top of the pyramid, so to speak, making the decision at the end, with these sorts of things being complementary to a large extent and focused on the mechanistic aspects as opposed to the the decision making and the critical aspects.
Yeah, it depends on the application. Obviously, if you've got your algorithms that are recommending what you should watch next on Netflix, then who cares? But if you've got someone making a decision on who to operate on, or in defense case, whether or not to launch a missile, yeah, you do need a person in the loop at some point in time. And the question is, where does that balance fit? And it might not be a static, human autonomy teaming thing. That might not be always the same mix between human and autonomy. But yeah, a person needs to make the decision in the end.
Correct.
Somehow.
Phil and JB, how is defence approaching this at the moment? Just to look at it from a different perspective.
Actually, yes, you go, Phil. Go on, you go first.
Okay.
I'm spoken too much.
Yeah. So I guess they're doing all sorts of research, looking out as far as, for example, 2040 and saying, well, what is the world going to look like in 2040? What systems might be out there that we will have to contend with and that we'll have to use? What technology will defence need to be familiar with, and how is that going to work? And then, what's the roadmap for getting there? So they're thinking about it in terms of that sort of time frame. I'm on a group at the moment which is just kicking off, looking at test and evaluation of systems, and they're thinking about, well, how do we test and evaluate and validate, verify a functioning of a system which has an artificial intelligence component to it. And I guess the corollary to that, as we talked about before, is you've got systems where people make decisions in the end. So how do you certify a system that's not purely technical, that there's a mixture of human and autonomous decision making involved in it? So it's going to get very complicated very quickly, and that's no different to anywhere else as well. I guess there's a bit of artificial intelligence being used, and I guess one of the points I was going to make was that artificial intelligence isn't machine learning. There's a whole bunch of different techniques. Machine learning is one, but defense in some of its IT systems is using AI a little bit. And I guess the other point is that there's always been a lot of autonomy in the last, I guess, in the computer age in certain weapon systems. So in one way, it's not a new topic to deal with, but there are a lot more complexities.
Yeah, just two points to add to Phil's. It covers pretty comprehensive coverage there, and that's one from a defense capability perspective, sensory perspective, and the other one from a training perspective. So from a sensory perspective, the biggest advancement that's happened in recent times, everyone's probably heard about this, right? F-35, 5th generation capability, and fundamental to that step up in these architectures and technologies is this recognition of the fact that no one view or individual view can give you the truth, right? To actually get a better picture of the truth, you need multiple. You get a better picture if you take multiple perspectives and you bring them together. And the concept of fusion and sensor fusion. So multiple sensors on different platforms, aircraft, ships, whatever, sensing the situation, and that information being used in real time to create a picture of what the real situation is. And that's the biggest step forward that's happened between 4th and 4.5 to 5th generation capabilities. Is previously each platform had its own sensors and their own thing, and they had to talk and exchange information over tactical data links and integrate that. And now the sensors are talking to themselves to come up with a picture of what's going on. And the platforms are just vehicles that carry these sensors around and create a picture of what's going on. So this concept of fusion is the recognition of the fact that no one perspective, or there's a risk that if you take one perspective, is probably not the right perspective. So bringing it back to the health thing, the concept of AI complementing the human is very much aligned with those concepts. And the second perspective in the defense perspective is from a training perspective. If you think about how defense does training, very good at the individual level, but that sophistication sort of drops off as you get more into the team and the joint and the collective level. Very high fidelity flight simulators, for example, to teach pilots how to fly. When you start talking about teams working together and training, or mission rehearsal being conducted across a joint capability, Army, Navy, Air Force, Special Forces working together to rehearse something, the actual capabilities that enables that is pretty limited. And the area where the limitation is the biggest is in the creation of computer-generated forces, the artificial intelligence behind creating synthetic entities that will behave as the real entity would. So while we have standards that can communicate state information, that can communicate common environments, there are no standards that exist that actually say how you model behaviors. And that's one of the biggest areas that challenge, and the correlation between what you talked about today in the AI construct, how do we actually model how something behaves from an AI perspective is really not understood or commonly established. And so the way the defense does it, they typically pick an application. They pick one vendor or they pick one way of doing it, and everyone does it the same way. And if you don't do it the same way, you just exchange state information, and typically you end up with problems. You end up with something doing something that the other guys are not doing, or they see things differently, and you end up with correlation issues. And so there's a big, I guess, an analogous situation or a challenge that's happening in defense as well. And the interesting thing is, it's the same core concepts. They're happening across the board, right? Technology has come to a point where it's forcing the vertical silos are breaking down because they're connecting where they didn't connect before. Data fusion, getting access to data now is becoming much more easy. Technologies are starting to get so connected that we haven't even thought of the ways that things could happen, and we get emergent properties happening. And that's the risk in these areas, is that we won't think of something, or we'll design something to do something, and then somewhere along the line, someone will use it for some other purpose, or it will create a relationship for some other purpose that will create an unintended consequence. And that's what we've got to protect against. And that's probably the biggest challenge we face in the AI construct, I think, is how we contain this, grow with it so that it becomes a benefit to society, as opposed to, I don't know, all the worst case theories of AI taking over the world, and we just become subject to subjugation, so to speak. Yeah. So.
Okay. Yeah, no, I guess I share a lot of the same concerns. Because you see, even the biggest companies, Microsoft, IBM, these people who have almost unlimited resources, and they still don't get it, and they're still making big mistakes, and they're still getting those unintended consequences. So, does anybody have one last question for Suj?
I think John's got one. He's come on.
I mean, you talk about the unintended consequences. I've heard in that, I don't know if this is true or not, but they've the stories of they gave talking about AI, like various supercomputers language, and they started talking to themselves, and then humans couldn't understand what they were talking about, and they started doing their own thing. And what do you do? And what are they talking about?
Exactly. Yes.
I think that was a true story too. I mean,
yeah, I think it was. Agreed. I can't remember the reference, but
they were talking about it's their own language, and then they started, what are they doing?
The possibilities that could go wrong is actually countless in that sense. Hence why you need to have some sort of human control.
Absolutely. Yeah. People make mistakes. Machines that people build mistakes. AI is not going to be any different. Exactly. So to expect it to be perfect is completely unrealistic. So definitely keeping an eye on it is the way to go.
And then you go to Asimov, and you start thinking about the
three laws of robotics.
Rules.
Yes.
Seriously.
Yeah, absolutely.
We start thinking about robot rules.
Yes.
Yep. There are people who are doing that, using those as the basis. Absolutely.
Okay. I think that's probably a good point to end it all on. Thanks to everybody for coming today, and thanks very much, Suj, for presenting and giving up your time.
Absolutely. Yes.
Excellent, mate.
It was a pleasure.
And this is a topic I'd love to revisit every 6 weeks or so, because I think we're scratching the surface, aren't we? Really?
Yeah.
Barely.
Barely scratching the surface.
Indeed, mate. Indeed.
Okay. Yeah, I hope everybody has a great weekend. Next week, the guest speaker is me. So
that'll be great. Yeah, looking forward to that.
I'll be at Games for Change next week, staying up all night for that. So I thought what I'd do is a bit of a session with a bit of a summary of what's happening in the Games for Change world. And also we've got plans to bring it to Melbourne at the end of next year. So I'll be sort of cherry picking all of the best ideas from all of the smart people that are speaking at that conference and bringing them back for people who don't want to stay up all night. So
Perfect.
That's of use to people.
Yeah, it sounds great.
Good work.
Thanks, Dale.
All right.
And we'll
Thanks,
get John on the panel at some point in time in August, you say. So we'll get back to you with something on that, John.
Yeah, August would be great. I'm a little bit swamped with some stuff.
Yeah, special breakfast edition.
Yep. We'll talk to you about it later. And thanks again,
Okay,
Suj.
great.
You're very welcome. My pleasure. I enjoyed it very much, and I really like the way that we bounce off ideas of each other, and then it actually is 1 + 1 is 3 or 4.
Absolutely. Yep. That's what systems engineering is about too, isn't it?
Absolutely. Yeah. Good plug there, Philip. Thank you. Excellent. Yeah.
Making 1 + 1 = 3. The sum of the whole is more than the sum of its parts.
Yes, indeed.
All right. On that note,
thank you all.
bye everyone. Have a great
Well done.
weekend.
Have a good weekend.
Bye.
Cheers.
See ya.
Cheers.
Bye.